Particles are waves. Waves don't have exact positions. And yet, every atom in your body knows precisely where it is. So here's the paradox. How does something spread out across space suddenly become here, solid enough to form atoms, chemistry, and the world you're sitting in right now? Max Born, one of the founders of quantum mechanics, calculated in 1926 that particles don't actually have definite positions. They only have probabilities of being found at specific locations when measured. Werner Heisenberg's uncertainty principle proved that position and momentum cannot be simultaneously determined with perfect precision, suggesting that the classical concept of a particle with definite location and velocity is fundamentally incorrect. Yet somehow, despite existing as probability waves, particles create a world of apparent solidity and definiteness. The chair you're sitting on feels solid because electrons maintain precise positions in chemical bonds. GPS satellites work because atomic clocks rely on electrons occupying exact energy levels. Computer processors function because electrons follow predictable paths through semiconductor materials. This paradox strikes at the heart of reality itself. If the fundamental constituents of matter are waves without definite positions, how does the classical world of definite objects emerge from quantum uncertainty? Why don't we see everyday objects existing in multiple positions simultaneously, like the quantum waves that compose them? Tonight, we're going to explore one of the deepest mysteries in physics: how definite positions emerge from indefinite waves. We'll journey through the strange mathematics of wave functions, examine the measurement problem that has puzzled physicists since Einstein, and discover how consciousness itself might play a fundamental role in creating the definite reality we experience. What we'll uncover challenges everything we think we know about the nature of existence. By the end of this investigation, you'll understand why some physicists believe that position is an illusion created by measurement, why others think that infinite parallel realities solve the paradox, and why a few radical thinkers propose that consciousness literally creates physical reality through the act of observation. The story begins with a simple experiment that shattered the classical view of matter forever. In 1909, physicist Geoffrey Taylor performed a version of the double-slit experiment using such faint light that only one photon at a time passed through the apparatus. Classical physics predicted that individual particles would pass through one slit or the other, creating two bright bands on a detection screen. Instead, Taylor observed something impossible. Even single photons created an interference pattern as if each particle had somehow passed through both slits simultaneously and interfered with itself. This single experiment proved that individual particles behave like waves, existing in multiple states until the moment they're detected. But here's what makes this genuinely disturbing. The moment you try to determine which slit the photon passed through, the interference pattern disappears. The act of measurement forces the photon to choose a definite path, collapsing its wave-like behavior into particle-like definiteness. It's as if reality exists in an indefinite state until consciousness observes it. This measurement problem has driven physicists to the edge of what's logically comprehensible. Niels Bohr argued that particles don't have definite properties independent of measurement. Albert Einstein famously objected, declaring that God does not play dice with the universe. Yet repeated experiments continue to confirm that quantum mechanics accurately predicts the behavior of particles that somehow exist as waves while maintaining definite positions when observed. Recent experiments have pushed the boundaries of this paradox to macroscopic scales. In 2010, researchers at UC Santa Barbara created quantum superposition in objects containing billions of atoms, demonstrating that even relatively large systems can exist in indefinite states until measured. The boundary between quantum uncertainty and classical definiteness remains mysterious. The practical implications extend far beyond academic physics. Quantum computers exploit the wave-like properties of particles to perform calculations impossible for classical computers. Quantum cryptography uses position uncertainty to create unbreakable communication codes. Medical imaging relies on quantum effects in atoms to reveal the internal structure of living tissue. Yet, despite these technological applications, the fundamental question remains unanswered. How do waves of probability become particles with definite positions? The mathematics of quantum mechanics describes the process with extraordinary precision, but the physical mechanism remains completely mysterious. If you're fascinated by the deepest puzzles of reality and want to explore how consciousness might literally create the physical world, subscribe and hit thumbs up. And here is a quantum thought experiment. If you could choose to exist as a wave spread across all possible positions, or as a particle with one definite location, which would you choose? Comment below, I'll pin the most mind-bending answer. Some interpretations of quantum mechanics suggest that particles never actually have definite positions. That definiteness is an illusion created by the limitations of observation. Other interpretations propose that all possible positions exist simultaneously in parallel universes, with consciousness selecting which reality we experience. Still others argue that the wave function is merely a mathematical tool that does not correspond to physical reality. The journey we're about to take will challenge your most basic assumptions about the nature of reality, matter, and consciousness. We'll explore why the quantum measurement problem might be unsolvable within current scientific frameworks, and what this tells us about the fundamental structure of existence. This isn't just about physics, it's about the nature of reality itself. The wave-particle duality that governs every atom in your body reveals something profound about how the universe creates the illusion of definiteness from a foundation of pure probability. Understanding this paradox might be the key to unlocking the deepest secrets of consciousness, reality, and our place within the cosmic order. The question of how waves become particles with definite positions isn't just a technical puzzle for physicists to solve. It is a window into the fundamental mystery of how anything definite can exist in a universe that appears to be built from pure uncertainty. Now, let's begin our journey into the quantum realm where waves and particles dance together in ways that challenge the very concept of definite existence. Chapter 1. Wave Reality. The first hint that particles might be waves came from one of the most beautiful experiments in the history of science. When Thomas Young shined light through two parallel slits in 1801, he expected to see two bright bands on a screen behind the slit's simple shadows cast by light traveling in straight lines like tiny particles. Instead, he observed something that would revolutionize our understanding of reality, an interference pattern of alternating bright and dark bands that could only be explained if light behaved like a wave. Young's double-slit experiment revealed that light waves passing through the two slits interfere with each other, creating regions where the waves add together to produce brightness and other regions where they cancel out to create darkness. This wave interference pattern provided definitive proof that light consists of waves rather than particles, settling a debate that had puzzled scientists since Newton's time. But the wave nature of light created its own puzzles. If light is a wave, what medium does it travel through? Waves in water require water, sound waves require air, but light travels through the apparent vacuum of space. 19th century physicists proposed that space must be filled with an invisible substance called the luminiferous ether that serves as the medium for light waves. The search for the ether led to the most famous failed experiment in physics. In 1887, Albert Michelson and Edward Morley designed an extraordinarily sensitive apparatus to detect Earth's motion through the ether by measuring tiny differences in the speed of light in different directions. Their interferometer could detect differences smaller than 1 part in a billion, yet they found absolutely no evidence for ether drift. The failure of the Michelson-Morley experiment created a crisis that ultimately led Einstein to propose special relativity in 1905. Einstein realized that light doesn't require a medium, it has a wave in the electromagnetic field itself, which exists as a fundamental feature of space and time. Light waves propagate as oscillating electric and magnetic fields that sustain each other through their mutual interaction. This electromagnetic field theory explained many properties of light with remarkable precision. James Clerk Maxwell's equations predicted that light waves should carry energy proportional to the square of their amplitude and should exert pressure on objects they encounter. Both predictions were confirmed by careful experiments, establishing that light definitely behaves as a wave phenomenon. However, Einstein's work on the photoelectric effect in 1905 revealed something troubling about the wave theory of light. When light shines on certain metals, it ejects electrons from the surface, but the energy of these photoelectrons depends on the frequency of light rather than its intensity. According to wave theory, brighter light should eject electrons with more energy, but experiments showed that brighter light only ejects more electrons, not more energetic ones. Einstein explained this puzzle by proposing that light consists of discrete packets of energy called photons, each carrying energy proportional to the light's frequency. The photoelectric effect occurs when individual photons transfer their energy to individual electrons, explaining why electron energy depends on photon frequency rather than light intensity. This photon hypothesis earned Einstein the Nobel Prize in 1921. But Einstein's photon theory created a new paradox. How could light be both a wave that creates interference patterns and a stream of particles that transfer energy in discrete packets? The wave-particle duality of light challenged the fundamental assumption that physical phenomena must be either waves or particles, not both simultaneously. The plot thickened when Louis de Broglie proposed in 1924 that if light waves could behave like particles, then particles might also behave like waves. De Broglie calculated that every particle should have a wavelength inversely proportional to its momentum. Particles with larger momentum would have shorter wavelengths, while particles with smaller momentum would have longer wavelengths. This seemed like pure theoretical speculation until Clinton Davison and Lester Germer confirmed de Broglie's prediction in 1927 by observing electron diffraction. When they fired electrons at a nickel crystal, the electrons created interference patterns characteristic of waves, proving that particles of matter exhibit wave-like behavior under appropriate conditions. The Davison-Germer experiment established that wave-particle duality isn't unique to light. It is a fundamental property of all matter and energy. Electrons, protons, neutrons, and even entire atoms create interference patterns when passed through appropriate double-slit experiments. The wave nature of matter is universal, but this universality makes the position problem even more puzzling. If electrons are waves, how do they occupy the precise positions required for chemical bonds? If atoms are waves, how do they maintain the definite structures needed for solid matter? If all particles are fundamentally waves, how does the classical world of definite positions emerge from quantum uncertainty? The mathematical framework of quantum mechanics, developed by Erwin Schrödinger and Werner Heisenberg in the 1920s, provides a precise method for calculating wave behavior in particles. Schrödinger's wave equation describes how the wave function of a particle evolves over time, while Heisenberg's matrix mechanics provides equivalent results using mathematical operators. The wave function contains all possible information about a particle's state, encoding probabilities for finding the particle at different positions when measured. The square of the wave function's amplitude at any point gives the probability density for detecting the particle at that location. This probabilistic interpretation, proposed by Max Born, explains how wave-like particles can appear to have definite positions when observed. Yet the wave function itself remains profoundly mysterious. Does it represent a real physical wave spreading through space, or is it merely a mathematical tool for calculating measurement probabilities? If it's physically real, how does it suddenly collapse to a definite position during measurement? If it's purely mathematical, how does it accurately predict the behavior of real particles? Consider an electron bound in a hydrogen atom. The electron's wave function describes a three-dimensional standing wave pattern around the nucleus, with different shapes corresponding to different energy levels. These orbital wave functions have definite mathematical forms, spherical, dumbbell-shaped, or more complex geometries that can be calculated precisely. But here's what makes this strange. The electron does not orbit the nucleus like a tiny planet. Instead, it exists as a probability cloud with the shape of its orbital wave function. The electron is simultaneously everywhere within this cloud, and nowhere in particular until something measures its position. Yet chemical bonds form when these probability clouds overlap in precise ways, suggesting that wave-like electrons somehow interact as if they have definite locations. The wave picture becomes even more bizarre when we consider that particles can exist in superposition states combinations of multiple wave functions simultaneously. An electron can exist in a superposition of being in multiple locations, multiple energy states, or multiple spin orientations until measurement forces it to choose a definite state. Recent experiments have demonstrated superposition in increasingly large systems. Researchers have created superposition states in molecules containing hundreds of atoms, showing that wave-like behavior isn't limited to microscopic particles. The boundary between quantum waves and classical particles remains mysterious and might not exist at all. The wave reality of particles forces us to abandon classical intuitions about matter and energy. In the quantum realm, particles don't travel along definite paths. They explore all possible paths simultaneously as waves. They don't have definite positions. They exist as probability clouds spread throughout space. They don't interact like billiard balls. They interfere with themselves and each other like overlapping waves. Yet somehow, from this foundation of pure uncertainty and wave-like probability, the classical world of definite objects emerges with remarkable consistency. Atoms maintain stable structures, molecules form predictable bonds, and solid matter exhibits reliable properties, despite being composed of wave-like particles that lack definite positions. This emergence of classical definiteness from quantum uncertainty represents one of the deepest puzzles in physics. The wave reality of particles has been confirmed by countless experiments, yet the mechanism by which waves create the illusion of definite positions remains completely mysterious. Understanding this transition from wave to particle might hold the key to understanding the nature of reality itself. Our next chapter explores how mathematical probability waves somehow transform into the definite positions we observe, and why this transformation might require consciousness itself to play a fundamental role in creating physical reality. Chapter 2. Probability clouds. The electron orbiting the nucleus of every atom in your body doesn't actually orbit at all. Instead, it exists as a three-dimensional probability cloud that surrounds the nucleus like a ghostly presence, with different regions of the cloud representing different chances of finding the electron at that location if you could somehow observe it. This probability cloud isn't just a mathematical convenience. It is the most accurate description of reality that physics can provide. When quantum mechanics describes an electron in a hydrogen atom, it doesn't give us a trajectory like the orbit of a planet around the sun. Instead, it provides a wave function that encodes the probability of finding the electron at every possible location around the nucleus. The square of this wave function S amplitude at any point represents the probability density, the likelihood of detecting the electron there during a measurement. These probability distributions have beautiful, precise mathematical forms that correspond to the electron's energy levels. The ground state of hydrogen creates a spherical probability cloud centered on the nucleus, with the highest probability of finding the electron at the Bohr radius of 0.529 angstroms. Higher energy levels create more complex shapes, dumbbell-shaped p orbitals, cloverleaf-shaped d orbitals, and even more elaborate, f orbitals. But here's what makes this profoundly strange. The electron isn't moving around within these probability clouds like a bee buzzing around a flower. The electron is the probability cloud. It exists in a quantum superposition of being at all possible locations simultaneously, with different amplitudes for different positions. The wave function doesn't describe where the electron is. It describes where it could be found if measured. This probabilistic existence creates the measurement problem that has puzzled physicists for nearly a century. Before measurement, the electron exists as a spread-out wave function encompassing multiple positions. During measurement, something causes the wave function to collapse to a single definite position. But what triggers this collapse? How does a probability wave become a definite particle? The mathematics of wave function collapse are precise, but provide no insight into the physical mechanism. When you measure an electron's position, the wave function instantaneously changes from a spread-out probability distribution to a sharply peaked function centered on the measurement result. This collapse happens faster than light could travel across the wave function, suggesting that it's not a physical process, but rather a change in our knowledge about the system. Yet experiments consistently confirm that unmeasured particles behave as if they genuinely spread out rather than having hidden definite positions. The quantum eraser experiments performed by researchers like Yoonho Kim demonstrate that particles can retroactively decide whether they were spread out or localized based on measurements made after they've already been detected. This suggests that the probability cloud description captures something fundamental about reality rather than just our ignorance. Consider the implications for the atoms in your body. Every electron in every atom exists as a probability cloud until something measures its position. Yet these probability clouds interact with extraordinary precision to form chemical bonds, create molecular structures, and enable the biochemical processes that sustain life. How do indefinite probability waves manage to create the definite structures required for complex chemistry? The answer lies in the mathematics of quantum interference. When probability waves from different electrons overlap, they don't simply add together. They interfere with each other in ways that can enhance or cancel probabilities in different regions of space. This interference creates stable patterns where certain electron configurations become highly probable while others become forbidden. Molecular orbital theory explains how atomic probability clouds combine to form the electron distributions in molecules. When two hydrogen atoms approach each other to form H, their electron probability clouds overlap and interfere. The interference pattern creates regions where the probability of finding electrons is enhanced, bonding orbitals, and other regions where the probability is reduced, antibonding orbitals. The molecule forms when electrons preferentially occupy the bonding orbitals. This process doesn't require the electrons to have definite positions. It emerges from the interference of probability waves. The chemical bond results from the quantum mechanical tendency of electrons to avoid each other while being attracted to both nuclei simultaneously. The stable molecular structure emerges from a delicate balance of probability distributions rather than from particles occupying fixed positions. But this raises deeper questions about the nature of physical structure. If molecules are built from probability waves rather than definite particle positions, what makes them appear solid and stable? How do probability clouds create the rigid structures we observe in crystals, the specific shapes of biological molecules, and the predictable properties of materials? The key insight comes from understanding that probability doesn't mean randomness in quantum mechanics. The Schrödinger equation determines how probability waves evolve with complete mathematical precision. Given the initial wave function of a system, you can calculate its future evolution exactly. The uncertainty lies not in the mathematics, but in the relationship between the wave function and observable reality. This deterministic evolution of probability creates stable patterns even though individual measurements remain unpredictable. The electron probability clouds in atoms maintain their shapes indefinitely because the Schrödinger equation preserves their form over time. Chemical bonds remain stable because the interfering probability waves that create them continue to interfere in the same way. Quantum mechanics reveals that stability emerges from probability rather than from mechanical rigidity. A diamond crystal isn't hard because its atoms are locked in fixed positions. It's hard because the probability waves of its electrons create interference patterns that strongly favor specific atomic arrangements, while making other arrangements extremely unlikely. The temperature dependence of materials provides another window into the probabilistic nature of matter. As temperature increases, atomic vibrations grow larger, causing the probability clouds of electrons to fluctuate more dramatically. Eventually, thermal energy overwhelms the quantum mechanical preferences that create stable structures, leading to phase transitions like melting or chemical decomposition. Even the sensation of touching a solid object results from probability wave interactions. When you press your finger against the table, you're not experiencing contact between definite particles. Instead, the electron probability clouds in your skin approach the electron probability clouds in the table surface. The Pauli exclusion principle, which prevents electrons from occupying the same quantum state, creates a repulsive force between these overlapping probability distributions. You feel this as the resistance of a solid surface. Recent advances in scanning tunneling microscopy and atomic force microscopy allow scientists to image individual atoms and their electron probability clouds. These images reveal the ghostly wave-like nature of matter at the smallest scales. Atoms appear as fuzzy probability distributions rather than discrete particles, confirming that the quantum mechanical description captures the true nature of matter. But perhaps the strangest aspect of probability clouds is their instantaneous response to measurement. When you measure an electron's position anywhere within its probability cloud, the entire wave function immediately collapses to that location. This happens regardless of how large the probability cloud might be. It could span meters or kilometers. Yet the collapse occurs simultaneously throughout its entire extent. This instantaneous collapse violates special relativity's prohibition against faster-than-light signaling, creating what Einstein called spooky action at a distance. The resolution of this paradox requires understanding that wave function collapse doesn't involve physical signals traveling through space. It represents a change in the quantum information encoded in the wave function itself. The measurement problem becomes even more puzzling when we consider that measurement devices are themselves composed of particles that exist as probability waves. How can a detector with its own quantum uncertainty measure the position of another uncertain particle? This leads to the infinite regress problem. If every measurement requires another measurement device, when does the chain of uncertainty finally end? Some interpretations of quantum mechanics propose that consciousness plays a special role in collapsing wave functions. In this view, probability clouds remain indefinite until conscious observation forces them to become definite. But this raises the disturbing possibility that physical reality depends fundamentally on conscious observers, that the universe exists in an indefinite state until consciousness creates definiteness through measurement. The probability cloud description of particles reveals that the classical concept of definite position might be an illusion created by the limitations of observation. Reality might consist fundamentally of overlapping probability waves that create the appearance of definite objects through the complex mathematics of quantum interference and measurement. Our next chapter explores how these indefinite probability waves somehow give rise to the definite measurements we observe, and why this transformation might represent the deepest mystery in all of physics. Chapter 3. Measurement Mystery. The act of measurement in quantum mechanics represents perhaps the strangest phenomenon in all of physics. When you measure the position of an electron that exists as a probability wave spread across space, something mysterious happens. the wave function instantaneously collapses from a distributed probability to a single definite location. But what exactly constitutes a measurement? How does the universe know when to stop being uncertain and start being definite? This measurement problem has haunted physics for nearly a century because it seems to require something outside the normal laws of physics to explain how indefinite quantum states become definite classical observations. The Schrödinger equation that governs quantum systems is completely deterministic and describes smooth, continuous evolution of probability waves. Yet measurement appears to involve sudden, discontinuous jumps from superposition to definiteness. Consider what happens when you measure an electron's position using a sophisticated detector. Before measurement, the electron exists in a superposition of being at many different locations simultaneously. The detector also exists in a superposition of different states corresponding to all possible measurement outcomes. When the electron interacts with the detector, quantum mechanics predicts that the combined system should exist in a superposition of all possible measurement results. But here's the paradox. We never observe superposition states in measurement devices. We always find the detector in a definite state, indicating a specific measurement result. Something must cause the combined electron detector system to collapse from superposition to a single definite outcome. But the Schrödinger equation provides no mechanism for this collapse. Eugene Wigner illustrated this problem with a thought experiment involving his friend in a laboratory. Wigner's friend measures the spin of an electron and observes a definite result, say, spin up. But from Wigner's perspective outside the laboratory, the entire system consisting of his friend, the electron, and the measurement apparatus should exist in superposition until Wigner himself opens the laboratory door and observes the result. This leads to the absurd conclusion: the conscious observation by Wigner is required to make his friend's measurement real. Before Wigner looks, his friend should exist in a superposition of having observed spin up and having observed spin down. Only when a conscious observer outside the system makes an observation does the wave function collapse and create definite reality. The Wigner's friend paradox reveals the deep conceptual problems with treating consciousness as special in quantum mechanics. If conscious observation is required for wave function collapse, then we need a precise definition of consciousness that distinguishes it from other physical processes. But no such definition exists, and attempts to create one lead to uncomfortable questions about the consciousness of animals, artificial intelligences, or even simple detection devices. Some physicists have proposed that measurement doesn't require consciousness, but instead occurs through the process of quantum decoherence. When a quantum system interacts with a large environment consisting of many particles, the delicate quantum correlations that maintain superposition are rapidly destroyed. This decoherence process effectively causes the wave function to collapse without requiring conscious observation. Wojciech Zurek's research on quantum decoherence has shown that macroscopic objects lose quantum coherence almost instantaneously when exposed to environmental interactions. A dust particle in air decoheres in about 10 to 31 seconds, while larger objects decohere even faster. This suggests that the classical world emerges naturally from quantum systems without requiring special measurement events. But decoherence theory faces its own problems. While decoherence explains why we don't observe quantum superposition in macroscopic systems, it doesn't explain why we observe specific measurement outcomes rather than others. Decoherence can explain why a detector doesn't remain in superposition, but it can't explain why the detector shows spin up rather than spin down in any particular measurement. The many worlds interpretation proposes a radical solution to the measurement problem. Wave function collapse never actually occurs. Instead, every possible measurement outcome happens in parallel branches of reality. When you measure an electron's position, the universe splits into multiple copies, one for each possible measurement result. You observe a definite outcome because you can only experience one branch of the universal wave function. In the many worlds picture, measurement doesn't create definiteness. It creates multiple realities where different outcomes occur. The electron doesn't collapse to a single position. Instead, different versions of you in different worlds observe the electron at different positions. The illusion of wave function collapse results from your inability to communicate with your parallel selves in other worlds. This interpretation eliminates the measurement problem by denying that measurements are special events. The universal wave function evolves according to the Schrödinger equation without any discontinuous collapses. What we interpret as measurements are simply branching events where the wave function splits into multiple, non-interacting components corresponding to different possible outcomes. However, the many worlds interpretation creates its own puzzles. If infinite parallel realities exist where all possible measurement outcomes occur, why do we observe the particular outcomes we do? What determines which branch of reality we experience? The theory provides no mechanism for selecting which of the infinite possible worlds becomes our observed reality. Alternative interpretations attempt to solve the measurement problem through different approaches. The pilot wave theory proposed by David Bohm suggests that particles always have definite positions guided by a quantum wave field. In this view, the wave function doesn't describe the particle's position, but rather influences how the particle moves through space. The pilot wave interpretation eliminates measurement-induced collapse by asserting that particles never exist in superposition. They always have definite positions. But these positions are guided by wave-like fields that we cannot observe directly. Measurement reveals the particle's pre-existing position rather than creating it through collapse. But pilot wave theory requires accepting the existence of unobservable guiding waves that influence particle behavior without being directly detectable. This hidden variable approach conflicts with Bell's theorem, which proves that any local hidden variable theory cannot reproduce all the predictions of quantum mechanics. The pilot wave theory avoids this conflict only by allowing instantaneous non-local influences between separated particles. Spontaneous collapse theories propose that wave function collapse occurs naturally without requiring measurement or consciousness. These theories modify the Schrödinger equation to include random collapse events that become more frequent for larger systems. Small systems like individual electrons rarely collapse, while large systems like measurement devices collapse almost continuously. The Girardi-Rimini-Weber theory suggests that each particle has a small probability of spontaneously collapsing per unit time. For systems containing many particles, the probability that at least one particle collapses becomes large, effectively causing the entire system to collapse into a definite state. This provides a natural mechanism for the emergence of classical behavior from quantum systems. However, spontaneous collapse theories face experimental challenges. The collapse events should release small amounts of energy that might be detectable in precise experiments. So far, no such energy release has been observed, placing strict limits on the parameters of collapse theories. The measurement problem becomes even more complex when we consider quantum computers, which exploit superposition states to perform calculations impossible for classical computers. Quantum computers maintain delicate superposition states in systems containing hundreds or thousands of quantum bits, yet they still produce definite computational results when measured. Recent experiments in quantum computing have revealed new aspects of the measurement problem. Researchers can now perform weak measurements that extract partial information about quantum systems without fully collapsing their wave functions. These measurements reveal that the transition from quantum to classical behavior might be gradual rather than sudden. The development of quantum error correction has also shed light on measurement problems. Quantum computers must constantly monitor their quantum states for errors while avoiding measurement-induced collapse. This requires sophisticated protocols that can detect errors without destroying the quantum information being protected. Perhaps the strangest aspect of the measurement problem is that it might be fundamentally unsolvable within current physics frameworks. If consciousness plays a role in wave function collapse, then explaining measurement requires understanding consciousness itself, a problem that remains far from solution in neuroscience and philosophy. The measurement mystery thus represents more than a technical problem in quantum mechanics. It reveals fundamental limitations in our understanding of the relationship between physical reality and conscious observation. The transition from indefinite quantum states to definite classical measurements might require new physics, new mathematics, or new ways of thinking about the nature of reality itself. Our next chapter explores how the precise mathematics of wave function somehow produces the stable atomic structures that make chemistry and life possible, despite the fact that particles lack definite positions until measured. Chapter 4. Atomic Architecture. Every atom in your body is a masterpiece of quantum architecture, built not from particles in definite positions, but from standing wave patterns that create stable structures through pure mathematical interference. The electrons that enable all chemistry do not orbit atomic nuclei like miniature planets. They exist as bays, three-dimensional probability clouds with shapes determined by the solutions to Schrödinger's wave equation. These atomic orbitals have precise geometric forms that emerge from the wave nature of electrons. The s orbitals are spherical, the p orbitals are dumbbell-shaped, the d orbitals resemble four-leaf clovers, and the f orbitals have even more complex geometries. But these aren't the paths that electrons follow. They read the shapes of the standing waves that electrons become when confined within atoms. The mathematics behind atomic structure reveals something extraordinary about how definite reality emerges from indefinite waves. When an electron is bound to an atomic nucleus, its wave function must satisfy specific boundary conditions that allow only certain wavelengths to exist as stable, standing wave patterns. These quantized wavelengths correspond to discrete energy levels, creating the step-like energy structure that makes atomic spectra possible. Consider the hydrogen atom, the simplest system where quantum waves create definite structure. The electron's wave function must approach zero at infinite distance from the nucleus and remain finite at the nucleus itself. These constraints restrict the possible wave functions to a discrete set of solutions, each with a specific energy level and spatial distribution. The ground state of hydrogen creates a spherical probability cloud with its peak at the Bohr radius 0.529 angstroms from the nucleus. This isn't arbitrary. It's the distance where the quantum mechanical uncertainty in the electron's kinetic energy exactly balances the electrostatic potential energy, creating a stable configuration that requires no energy input to maintain. But here's what makes this strange. The electron doesn't exist at the Bohr radius. It exists as a probability wave distributed throughout the entire volume around the nucleus, with the highest probability density at the Bohr radius. The atom has a definite size determined by quantum mechanics, yet the electron that determines this size has no definite position. The wave function's shape also determines the atom's chemical properties. The s orbitals are spherically symmetric, making cell electrons equally likely to interact with neighboring atoms from any direction. The p orbitals have directional lobes, creating preferential bonding directions that determine molecular geometries. The complex shapes of d and f orbitals enable the rich chemistry of transition metals and rare earth elements. This connection between wave function geometry and chemical behavior reveals how indefinite quantum waves create definite molecular structures. When atoms approach each other, their electron wave functions begin to overlap. The interference between these overlapping waves creates new probability distributions that can either enhance or suppress the likelihood of finding electrons in the region between nuclei. Bonding molecular orbitals form when wave function interference enhances electron probability between nuclei, creating attractive forces that hold atoms together. Antibonding orbitals form when interference reduces electron probability between nuclei, creating repulsive forces that push atoms apart. Chemical bonds emerge from the quantum mechanical preference for electrons to occupy bonding rather than antibonding orbitals. The mathematics of molecular orbital theory explain how indefinite probability waves create the definite structures of molecules. The wave functions of individual atoms combine according to precise mathematical rules that determine the shapes and energies of molecular orbitals. These calculations predict bond lengths, bond angles, and molecular properties with remarkable accuracy. Yet the underlying physical picture remains deeply mysterious. How do probability waves know to form stable molecular configurations? How does the interference of indefinite wave functions create the definite geometries we observe in crystals and biological molecules? The mathematics work perfectly, but the physical mechanism remains incomprehensible. Consider the benzene molecule, where 6 carbon atoms form a regular hexagon with carbon-carbon bonds that are all identical in length and strength. Classical chemistry struggled to explain this structure because benzenes seem to require alternating single and double bonds that should create an irregular hexagon with bonds of different lengths. Quantum mechanics reveals that benzene s electrons exist in the localized molecular orbitals that extend around the entire ring structure. The electron probability clouds form symmetric patterns that make all carbon-carbon bonds equivalent. The definite hexagonal structure emerges from indefinite electron waves that are spread symmetrically around the molecule. The stability of benzene results from resonance, the quantum mechanical averaging over multiple possible electron configurations. The electrons don't rapidly switch between different bonding patterns. Instead, they exist in a superposition state that represents all possible configurations simultaneously. This quantum superposition creates a more stable structure than any single classical bonding pattern could achieve. DNA provides an even more striking example of how quantum waves create definite biological structures. The double helix structure depends on precise hydrogen bonding between complementary base pairs. Yet these hydrogen bonds form through quantum mechanical interactions between electron probability clouds, rather than through classical electrostatic forces between definite charges. The specificity of DNA base pairing emerges from the quantum mechanical shapes of molecular orbitals in adenine, thymine, guanine, and cytosine. These shapes determine how electron probability clouds can overlap to form stable hydrogen bonds, creating the lock and key complementarity that enables genetic information storage and replication. Recent advances in scanning tunneling microscopy have allowed scientists to image individual molecular orbitals, revealing the ghostly wave-like nature of the electrons that create molecular structure. These images show that electrons exist as fuzzy probability clouds with the precise shapes predicted by quantum mechanical calculations. But perhaps the most remarkable aspect of atomic architecture is how it maintains stability despite being built from fundamentally uncertain components. Individual electron measurements reveal random positions within probability clouds, yet the overall atomic structure remains constant. How do random quantum events create non-random macroscopic stability? The answer lies in the statistical nature of quantum mechanics. While individual measurements are unpredictable, the probability distributions that govern these measurements are completely deterministic. The Schrödinger equation specifies exactly how probability clouds evolve over time, creating stable patterns even though individual particle positions remain uncertain. This statistical stability explains how quantum uncertainty at the microscopic scale gives rise to predictable behavior at larger scales. A piece of copper wire conducts electricity reliably because the statistical properties of its electron probability clouds remain constant, even though individual electrons follow unpredictable quantum paths. The temperature dependence of atomic structure provides another window into how quantum waves create definite properties. As temperature increases, thermal energy causes atomic vibrations that modulate the electron probability clouds. Eventually, thermal fluctuations become large enough to disrupt the quantum mechanical preferences that create stable structures, leading to phase transitions like melting or chemical decomposition. Quantum mechanics also explains the periodic table's organization, showing how electron wave functions in different atoms create the recurring patterns of chemical properties. As atomic number increases, additional electrons fill orbitals in a specific order determined by quantum mechanical energy calculations. The periodic repetition of electron configurations creates the periodic repetition of chemical properties. The noble gases provide a perfect example of how electron wave function patterns determine chemical behavior. Helium, neon, argon, and other noble gases have completely filled electron shells that create spherically symmetric probability clouds with no preferential bonding directions. This quantum mechanical symmetry explains their chemical inertness. Transition metals exhibit more complex behavior because their d orbital electrons create intricate probability cloud patterns that can interact in multiple ways with other atoms. The varied shapes of d orbitals, some pointing between atoms, others pointing directly at neighboring atoms, create the rich coordination, chemistry, and catalytic properties that make transition metals essential for biological processes. The quantum mechanical picture of atomic architecture reveals that the solid matter we experience emerges from a foundation of pure mathematical abstraction. Atoms are in tiny solar systems with particles orbiting nuclei, by they standing wave patterns whose geometric forms are determined by the solutions to differential equations. The definite structures of molecules, crystals, and living systems all emerge from the interference patterns of probability waves. Yet somehow, these abstract mathematical entities create the tangible reality we experience. The wave functions that describe atomic structure are mathematical objects that exist in abstract quantum mechanical Hilbert space, yet they determine the properties of every material object in the universe. The relationship between mathematical abstraction and physical reality becomes utterly mysterious when viewed from the quantum perspective. Our next chapter explores how these stable atomic wave patterns give rise to the dynamic processes of chemistry, where indefinite probability clouds somehow orchestrate the definite reactions that power life itself. Chapter 5. Chemical Choreography. Every chemical reaction is a dance of probability waves, where electron clouds from different atoms overlap, interfere, and rearrange themselves into new molecular configurations without any particles ever having definite positions. The chemistry that sustains life creates materials, and powers technology emerges from the quantum mechanical choreography of indefinite wave functions that somehow produce highly definite outcomes. When two hydrogen atoms approach each other to form an H molecule, their electron wave functions begin to overlap before the atoms are close enough for any classical interaction. The quantum mechanical description reveals that the electrons don't wait for the atoms to touch. They start influencing each other through wave function interference when they are still separated by distances much larger than the atoms themselves. As the hydrogen atoms move closer, their overlapping wave functions create new probability distributions that didn't exist for the isolated atoms. The interference can be either constructive, enhancing the probability of finding electrons between the nuclei, or destructive, reducing this probability. Constructive interference creates bonding molecular orbitals that lower the system's energy, while destructive interference creates anti-bonding orbitals that raise the energy. The formation of the hydrogen molecule occurs when electrons preferentially occupy the lower energy bonding orbital, creating an attractive force between the nuclei. But here is what makes this process mysterious. The electrons don't move from atomic orbitals to molecular orbitals. Instead, the probability wave descriptions change continuously as the atoms approach, creating new quantum states that are neither purely atomic nor purely molecular during the transition. The kinetics of chemical reactions reveal even stranger aspects of how probability waves orchestrate definite changes. Transition state theory describes how reactant molecules must overcome energy barriers to become products. But quantum mechanics shows that particles can tunnel through these barriers rather than going over them. This quantum tunneling allows chemical reactions to occur, even when the reactants lack sufficient thermal energy to overcome the classical energy barrier. Enzymatic reactions in biological systems rely heavily on quantum tunneling to achieve the extraordinary efficiency and selectivity that make life possible. The enzyme catalase, for example, decomposes hydrogen peroxide at rates approaching the theoretical limit for diffusion-controlled reactions. This efficiency requires the enzyme to lower activation barriers and enable quantum tunneling pathways that would be impossible in classical systems. Recent studies of photosynthesis have revealed that quantum coherence plays a crucial role in the near-perfect efficiency of energy transfer in photosynthetic complexes. When light hits a chlorophyll molecule, the absorbed energy exists in a quantum superposition of being on multiple molecules simultaneously. This quantum coherence allows the energy to explore all possible pathways through the photosynthetic antenna complex and find the most efficient route to the reaction center. The quantum coherence in photosynthesis per surprisingly long times, hundreds of femtoseconds, despite the warm, noisy environment of living cells. This suggests that biological systems have evolved to exploit quantum mechanical effects for enhanced performance, challenging the assumption that quantum coherence is too fragile to play important roles in biology. Even more remarkably, recent experiments have detected quantum coherence in avian navigation, where birds appear to use quantum entanglement in cryptochrome proteins to sense magnetic fields for migration. The quantum compass mechanism involves electron pairs in excited cryptochrome molecules that exist in entangled spin states sensitive to magnetic field direction. This quantum effect might explain how birds navigate with extraordinary precision over thousands of miles. The wave nature of particles creates another puzzling aspect of chemical behavior. How do chemical reactions produce definite stoichiometric ratios when the reactants exist as indefinite probability clouds? When you combine hydrogen and oxygen gases to form water, you consistently get 2 hydrogen atoms per oxygen atom, despite the fact that individual atoms don't have definite positions until measured. The answer lies in the quantum mechanical selection rules that govern which reactions are allowed and which are forbidden. These rules emerge from the symmetry properties of molecular wave functions and determine how electron probability clouds can rearrange during chemical transformations. Only certain combinations of reactant wave functions can evolve into stable product configurations. Consider the reaction that forms water from hydrogen and oxygen. The molecular orbital description shows that the oxygen atom ssp3 hybrid orbitals can overlap with hydrogen 1 south orbitals in only specific geometric arrangements. The quantum mechanical constraints on these overlaps determine that water molecules must have a bent structure with a specific bond angle of 104.5 degrees. This precise molecular geometry emerges from the wave interference patterns of electron probability clouds, not from any classical mechanical forces between particles. The definite shape of water molecules results from indefinite quantum waves that can only combine in certain mathematical patterns, allowed by the symmetries of the Schrödinger equation. The catalytic cycles that drive biochemistry reveal how quantum waves can create complex, multi-step processes with extraordinary precision. Hemoglobin's oxygen binding mechanism involves quantum mechanical changes in the iron atom S electron configuration that alter the protein S shape and oxygen affinity. The wave function changes propagate throughout the protein structure, creating cooperative effects where binding one oxygen molecule affects the binding affinity for subsequent molecules. These conformational changes in proteins demonstrate how quantum mechanical effects at the atomic scale can influence biological function at much larger scales. The electron wave function changes in hemoglobin. S-heme groups create mechanical forces that alter the protein's tertiary structure, showing how indefinite quantum states translate into definite biological actions. Phase transitions in chemical systems provide another example of how quantum waves create definite macroscopic changes. When ice melts to form liquid water, the process involves breaking hydrogen bonds between water molecules. But these hydrogen bonds exist as quantum mechanical probability distributions rather than classical electrostatic attractions between definite charges. The melting transition occurs when thermal energy overcomes the quantum mechanical preferences that maintain the ice crystal structure. The electron probability clouds that create hydrogen bonds become more dynamic as temperature increases, eventually reaching a point where the quantum mechanical stabilization of the crystal lattice can no longer compete with thermal motion. Superconductivity represents perhaps the most dramatic example of how quantum waves can create definite macroscopic properties. In superconductors, electrons form Cooper pairs that exist in a quantum superposition state extending throughout the entire material. This macroscopic quantum coherence eliminates electrical resistance and creates perfect diamagnetism. The wave function describing a superconductor's Cooper pairs can extend over distances measured in centimeters or even meters, creating quantum coherence at macroscopic scales. When current flows through a superconductor, it flows as a single quantum mechanical wave rather than as individual particle motions. This quantum current can persist indefinitely without energy dissipation. Chemical bonding in extended systems like metals and semiconductors reveals how quantum waves create the electronic properties that enable modern technology. In crystalline silicon, electron wave functions extend throughout the entire crystal lattice, creating energy bands rather than discrete molecular orbitals. The band structure determines whether the material is a conductor, semiconductor, or insulator. The wave nature of electrons in solids explains phenomena like electrical conductivity, thermal conductivity, and optical properties that would be incomprehensible from a classical particle perspective. When light interacts with a metal surface, it excites electron waves that can propagate throughout the material, creating surface plasmons and other collective quantum phenomena. Recent advances in single-molecule spectroscopy have allowed scientists to observe chemical reactions in real time, revealing the quantum mechanical details of how molecular transformations occur. These experiments show that chemical bonds don't break and form instantaneously. Instead, the electron probability distributions evolve smoothly through intermediate configurations that represent neither reactants nor products. The quantum mechanical picture of chemistry reveals that chemical reactions are fundamentally about information processing rather than mechanical rearrangements. The wave functions that describe reactants contain information about possible product states, and chemical reactions represent the processing of this quantum information according to the rules of quantum mechanics. This informational view of chemistry suggests that molecular systems might be capable of quantum computation, using chemical bonds as quantum bits and chemical reactions as quantum logic gates. Some researchers have proposed that biological systems might exploit this quantum computational capacity for enhanced information processing in neural networks and other complex biological systems. The chemical choreography of probability waves thus creates all the definite processes we observe in chemistry and biology, from the precision of enzyme catalysis to the efficiency of photosynthesis to the conductivity of metals. Yet the mechanism by which indefinite quantum waves produce these definite chemical behaviors remains as mysterious as the measurement problem itself. Our next chapter examines how quantum mechanics forces us to reconsider the very concept of definite position, and whether location might be a feature that only emerges through the process of observation rather than existing as an intrinsic property of particles. Chapter 6. Position paradox. The concept of position becomes paradoxical in quantum mechanics because particles don't seem to have definite locations until we measure them, yet they somehow interact with each other and form stable structures as if they do have definite positions. This paradox strikes at the heart of our understanding of what it means for something to exist at a particular place in space. Heisenberg's uncertainty principle provides the mathematical framework for understanding positional indefiniteness. The principle states that the product of uncertainties in position and momentum must always exceed Planck's constant divided by 4. This isn't just a limitation of measurement technology. It is a fundamental property of quantum systems that prevents particles from simultaneously having perfectly definite position and momentum. But the uncertainty principle raises deeper questions about the nature of position itself. If a particle cannot have a perfectly definite position, does position exist as a property of particles independent of measurement? Or is position something that emerges only through the interaction between particles and measuring devices? Consider an electron bound in a hydrogen atom. Before measurement, quantum mechanics describes the electron as existing in a superposition of all possible positions around the nucleus, with different probability amplitudes for different locations. The electron doesn't have a definite position. It has a probability distribution of possible positions encoded in its wave function. When you measure the electron's position, something remarkable happens. The measurement process forces the electron to choose a specific location from its probability distribution. The wave function collapses from a spread-out superposition to a localized spike centered on the measurement result. But this raises the question, did the electron have that position before measurement? Or did the measurement create the position? Bell's theorem and subsequent experimental tests have provided strong evidence that particles do not have pre-existing definite positions prior to measurement. If electrons had hidden definite positions that were simply revealed by measurement, then certain statistical correlations between measurements should be impossible. Yet experiments consistently observe these impossible correlations, suggesting that position is created by measurement rather than revealed by it. The delayed choice quantum eraser experiments performed by researchers like Yoon-ho Kim push this conclusion to even more disturbing territory. These experiments show that a particle's position history can be retroactively determined by measurements made after the particle has already been detected. A particle can decide whether it had a definite position or existed in superposition based on measurements that occur in its future. This temporal non-locality of quantum measurement suggests that position might not be a property that particles possess at specific times. Instead, position might be a relational property that emerges from the entire causal structure of a measurement process, including events that occur after the particle has apparently been detected. The phenomenon of quantum tunneling provides another perspective on the position paradox. When particles tunnel through energy barriers, they appear to cross regions of space where they cannot classically exist. Quantum mechanical calculations show that tunneling particles have zero probability of being found inside the barrier region, yet they somehow manage to get from one side to the other. This suggests that particles might not travel through space in the classical sense of moving continuously from one position to another. Instead, quantum mechanics describes particle motion as the evolution of probability waves that can exhibit non-classical behaviors like tunneling. The particle doesn't have a definite trajectory through space. Its wave function simply evolves from one configuration to another. Recent experiments with ultra-cold atoms trapped in optical lattice have revealed new aspects of the position paradox. Researchers can create quantum superposition states where individual atoms exist at multiple lattice sites simultaneously. These atoms can be made to tunnel between sites, interfere with themselves, and exhibit other quantum behaviors that are incompatible with having definite positions. But when researchers measure which lattice site contains a particular atom, they always find the atom at a single definite location. The superposition state collapses to a specific position, and subsequent measurements confirm that the atom remains at that location until it's perturbed by another interaction. This raises questions about the persistence of position after measurement. If measurement creates definite position where none existed before, how long does this definiteness last? Quantum mechanics suggests that position measurements create temporary definiteness that gradually evolves back into indefiniteness as the particle S-wave function spreads out over time. The spreading of wave functions after measurement reveals another strange aspect of quantum position. Even after a precise position measurement, a particle's wave function immediately begins to spread according to the Schrödinger equation. The more precisely you measure position initially, the faster the wave function spreads. Reflecting the uncertainty principle's constraint, the precise position implies uncertain momentum. This suggests that definite position is inherently unstable in quantum mechanics. Even perfect position measurements create only momentary definiteness that immediately begins to decay back into indefiniteness. Position might be better understood as a transient property that requires continuous measurement to maintain. The quantum Zeno effect provides experimental confirmation of this idea. When quantum systems are measured frequently enough, the repeated measurements can freeze the system's evolution, preventing it from changing states. This suggests that maintaining definite properties requires continuous measurement. Without constant observation, quantum systems evolve back into superposition states. Quantum field theory adds yet another layer of complexity to the position paradox. In relativistic quantum mechanics, particles can be created and destroyed, making the concept of tracking a particle's position over time meaningless. What we interpret as particle motion might actually be the continuous creation and annihilation of particle-antiparticle pairs in the quantum vacuum. The Casimir effect demonstrates that even empty space contains quantum fluctuations that can exert measurable forces on physical objects. These vacuum fluctuations suggest that the concept of definite position becomes problematic, even for the space itself. The quantum vacuum exists in a superposition of containing different numbers of virtual particles at different locations. String theory proposes an even more radical revision of the position concept by suggesting that the fundamental constituents of matter are one-dimensional strings rather than point particles. In string theory, position becomes a property of string configurations rather than particle locations, and the apparent point-like nature of particles emerges only at low energies where string effects are negligible. The holographic principle suggests that all the information contained within a volume of space might be encoded on its boundary surface. If this is true, then the concept of particles having definite positions within the volume becomes questionable. Position might be better understood as information encoded on boundaries rather than as intrinsic properties of objects. Loop quantum gravity approaches the position paradox from yet another angle by proposing that space itself has a discrete quantum structure at the Planck scale. In this theory, position becomes quantized like energy levels in atoms, and the continuous space of classical physics emerges only as an approximation valid at larger scales. These various approaches to the position paradox suggest that our classical concept of definite spatial location might be fundamentally inadequate for describing quantum reality. Position might not be an intrinsic property of particles, but rather an emergent feature that appears only through the process of measurement and observation. The implications extend beyond physics to questions about the nature of existence itself. If particles don't have definite positions independent of measurement, then the material objects we experience as having definite locations must somehow emerge from indefinite quantum foundations. The solidity and definiteness of everyday reality becomes a kind of collective illusion created by the statistical behavior of countless indefinite quantum systems. Yet this illusion is remarkably stable and persistent. The chair you're sitting on maintains its shape and position, despite being composed of particles that lack definite positions. The computer processing these words functions reliably despite being built from electrons that exist as probability waves. How does collective indefiniteness create individual definiteness? The position paradox thus reveals fundamental limitations in our conceptual frameworks for understanding reality. Classical concepts like location and definite position might be approximations that work well at macroscopic scales, but break down when applied to the quantum foundations of matter. Understanding how definite positions emerge from indefinite quantum states might require developing entirely new ways of thinking about space, time, and existence itself. Our next chapter explores how the apparent collapse of wave functions during measurement might actually represent the branching of reality into multiple parallel worlds, each containing different definite outcomes for the same quantum measurement. Chapter 7. Reality branching. The many worlds interpretation of quantum mechanics offers a radical solution to the position paradox. Particles don't collapse from indefinite waves to definite positions during measurement. Instead, reality branches into multiple parallel worlds where different measurement outcomes occur simultaneously. Every quantum measurement creates new universes, each containing observers who measure different definite results from the same initial superposition state. When you measure an electron's position, you don't force it to choose a single location from its probability distribution. Instead, the universal wave function branches into multiple components, each corresponding to a different possible measurement outcome. One version of you observes the electron at position A in one branch of reality, while another version observes it at position B in a different branch, and so on for all possible measurement results. This interpretation was first proposed by Hugh Everett III in his 1957 doctoral thesis, though it wasn't called many worlds until later popularization by Bryce DeWitt. Everett realized that if you take the mathematical formalism of quantum mechanics seriously, without adding special collapse postulates, then the universal wave function must evolve according to the Schrödinger equation at all scales. This deterministic evolution naturally leads to branching rather than collapse. The mathematics of many worlds theory are surprisingly straightforward. When a quantum system in superposition interacts with a measurement device, the combined system evolves into a superposition of all possible measurement outcomes. Each component of this superposition corresponds to a different branch or world where a specific result occurs. The observer, being part of the system, also exists in superposition across all branches. But here's what makes this interpretation both elegant and disturbing. Each branch contains observers who experience only one definite measurement result and remain unaware of the other branches. From the perspective of any individual observer, quantum measurements appear to produce random definite outcomes, exactly as predicted by conventional quantum mechanics. The branching remains hidden because observers cannot communicate across different branches. Consider a quantum measurement where an electron has equal probability of being found at position X or position Y. In the conventional interpretation, the electron randomly chooses one position when measured, with 50% probability for each outcome. In the many worlds interpretation, both outcomes occur in parallel branches of reality. One version of you measures position X, while another version measures position Y, each believing their result was randomly selected. The many worlds interpretation eliminates the measurement problem by denying that wave function collapse ever occurs. Instead of mysterious discontinuous jumps from superposition to definiteness, the universal wave function evolves smoothly and deterministically according to the Schrödinger equation. What appears to be collapse is actually decoherence, the loss of quantum interference between different branches as they become entangled with their environments. Quantum decoherence explains why observers in different branches cannot communicate with each other. When measurement creates multiple branches, each branch becomes entangled with different environmental states. This entanglement effectively destroys the quantum interference between branches, making them evolve independently like separate classical realities. Wojciech Zurek's research on quantum decoherence has shown that this process occurs extremely rapidly for macroscopic systems. A measurement device loses quantum coherence with alternative measurement outcomes in timescales far shorter than human perception. This explains why we experience definite measurement results rather than quantum superposition by the time we become aware of a measurement. Decoherence has already separated the branches. But the many worlds interpretation raises profound questions about personal identity and the nature of conscious experience. If every quantum measurement creates multiple versions of you experiencing different outcomes, which version is the real you? Are all versions equally real, or is there something special about the branch you happen to experience? The theory suggests that there's nothing special about your particular branch of reality. All branches are equally real and contain conscious observers who believe their experiences are unique. Your sense of being a single continuous self is an illusion created by the fact that you can only experience one branch at a time. Countless other versions of you exist in parallel branches, each with slightly different histories of quantum measurement outcomes. This multiplicity of selves becomes staggering when you consider how many quantum measurements occur each second. Every radioactive decay, every photon absorption, every collision between particles creates new branches of reality. David Deutsch estimates that the number of parallel worlds increases exponentially with time, reaching incomprehensibly vast numbers within fractions of a second. If many worlds theory is correct, then the branching process that creates definite positions from indefinite waves is occurring continuously throughout your body. Every quantum event in your neurons creates parallel versions of your consciousness with slightly different thoughts and experiences. The stream of consciousness you experience is just one path through an exponentially branching tree of possible mental states. This has disturbing implications for free will and moral responsibility. If every possible choice you could make occurs in some branch of the multiverse, do your decisions actually matter? Is there moral significance to your actions if alternative versions of you make all possible choices simultaneously? The many worlds interpretation suggests that every possible version of your life plays out somewhere in the vast ensemble of parallel realities. Some philosophers argue that this makes moral choices meaningless, while others contend that it makes them infinitely important. If every possible action occurs somewhere, then perhaps the goal isn't to make the right choice, but to influence which types of realities become more probable through the mathematical structure of quantum branching. The preferred basis problem poses another challenge for many worlds theory. The interpretation assumes that reality branches along specific lines corresponding to definite measurement outcomes. But quantum mechanics provides no fundamental reason why reality should branch into states with definite positions, rather than states with definite momenta or other properties. The choice of which properties become definite appears arbitrary. Decoherence theory partially addresses this problem by showing that environmental interactions naturally select certain properties as classical. Position and momentum become classical because they couple strongly to environmental degrees of freedom, while more abstract quantum properties remain quantum because they don't interact significantly with the environment. Recent experiments with quantum computers have begun to test the boundaries of many worlds theory by creating and manipulating superposition states in increasingly complex systems. These experiments demonstrate that quantum superposition can persist in systems containing thousands of quantum bits, supporting the idea that macroscopic superposition states are possible in principle. But quantum computing also reveals practical limits to maintaining superposition. Even the most sophisticated quantum computers must constantly correct errors caused by environmental decoherence. This suggests that while many worlds theory might be mathematically correct, the different branches of reality become effectively isolated almost immediately after they form. The quantum suicide thought experiment illustrates some of the stranger implications of many worlds theory. In this scenario, a person uses a quantum random generator to determine whether a lethal device activates. Many worlds theory predicts that branches where the device activates exist alongside branches where it doesn't. From the perspective of the person involved, they can only experience the branches where they survive, potentially leading to the subjective experience of immortality. While this thought experiment is purely theoretical, it highlights how many worlds theory challenges conventional thinking about probability and survival. If all possible outcomes occur in parallel branches, then the subjective experience of any conscious observer is necessarily biased toward branches where they continue to exist. The cosmological implications of many worlds theory are equally mind-bending. If every quantum event creates new branches of reality, then the universe is constantly splitting into an enormous ensemble of parallel cosmologies. Every possible history consistent with quantum mechanics occurs somewhere in this multiverse, including histories where the fundamental constants of physics take different values. This suggests that the apparent fine-tuning of our universe for the existence of life might be explained anthropically. We necessarily find ourselves in a branch of reality where the constants allow for our existence, regardless of how improbable such a universe might be. The vast majority of branches might be sterile, but conscious observers can only exist in the tiny fraction of branches where conditions permit the emergence of complexity. The many worlds interpretation thus transforms the position paradox from a problem about wave function collapse to a problem about the branching structure of reality. Particles don't transition from indefinite waves to definite positions. Instead, indefinite quantum states evolve into superpositions of multiple definite realities. Position becomes definite not through collapse but through branching, with each branch containing observers who experience one specific outcome from the original superposition. Yet this solution raises equally profound questions about the nature of existence, consciousness, and reality. If infinite parallel worlds exist where all possible measurement outcomes occur, then understanding quantum mechanics becomes inseparable from understanding the fundamental nature of consciousness and its role in selecting which branch of reality we experience. Our next chapter explores whether consciousness plays a special role in quantum mechanics, and whether the act of conscious observation might be what transforms indefinite quantum states into the definite reality we experience. Chapter 8. Consciousness Connection. The relationship between consciousness and quantum mechanics remains one of the most controversial and profound questions in modern science. If particles exist as indefinite probability waves until measured, and if measurement somehow creates definite positions, then what constitutes measurement? Some interpretations suggest that consciousness itself plays a fundamental role in collapsing wave functions and creating the definite reality we experience. This consciousness-based interpretation of quantum mechanics emerged from the work of mathematicians like John von Neumann and Eugene Wigner in the 1930s and 1940s. They realized that the measurement problem creates an infinite regress. If measurement devices are themselves quantum systems existing in superposition, then measuring a quantum system simply creates a larger superposition that includes both the original system and the detector. Von Neumann's analysis suggested that this regress must terminate somewhere. There must be something that's not governed by quantum mechanics and can collapse wave functions without itself existing in superposition. He proposed that consciousness might serve this role, existing outside the quantum mechanical description and possessing the special ability to select definite outcomes from quantum superpositions. Wigner developed this idea further with his famous Wigner's friend thought experiment. If quantum mechanics applies to all physical systems, then a friend performing a quantum measurement in an isolated laboratory should exist in superposition until an external observer opens the laboratory and observes the result. Wigner suggested that consciousness prevents this absurd conclusion by collapsing wave functions through the act of conscious observation. But defining consciousness precisely enough to play this role in physics proves extraordinarily difficult. What distinguishes conscious observation from mechanical detection? Does consciousness require self-awareness, or is any information processing system sufficient? Can artificial intelligence systems collapse wave functions, or is there something special about biological consciousness? These questions become particularly acute when we consider the neural basis of consciousness. Modern neuroscience views consciousness as an emergent property of complex information processing in neural networks. But neural networks are physical systems governed by quantum mechanics, composed of atoms whose electrons exist as probability waves until measured. If consciousness emerges from quantum mechanical brain processes, then consciousness itself should exist in superposition until observed by another conscious system. This leads to the paradox that consciousness cannot serve as the foundation for wave function collapse if consciousness itself requires wave function collapse to exist. Roger Penrose and Stuart Hameroff have proposed a radical solution to this paradox through their orchestrated objective reduction, OR theory. They suggest that consciousness arises from quantum processes in neural microtubules protein structures that maintain the shape and organization of neurons. In their model, consciousness involves quantum superposition states in these microtubules that collapse spontaneously when they reach a critical threshold. The OR theory proposes that consciousness involves quantum computation in microtubule networks throughout the brain. These quantum computations exist in superposition until they spontaneously collapse due to gravitational effects, creating moments of conscious experience. Each conscious moment corresponds to the collapse of a quantum superposition state in the brain's microtubule network. If this theory is correct, then consciousness might indeed play a special role in quantum mechanics, not because conscious observation collapses external wave functions, but because consciousness itself results from quantum wave function collapse in neural systems. The definite nature of conscious experience would emerge from the same fundamental process that creates definite positions for particles. But OR theory faces significant challenges. Most neuroscientists argue that quantum coherence cannot survive in the warm, noisy environment of biological tissue. Quantum decoherence times in neural tissue are estimated to be much shorter than the timescales relevant for neural computation, making it unlikely that quantum effects play important roles in brain function. Recent experiments have begun to test these assumptions by looking for quantum effects in biological systems. Researchers have discovered quantum coherence in photosynthesis, where energy transfer efficiency appears to benefit from quantum superposition states that persist for surprisingly long times in complex biological environments. These discoveries suggest that biology might be more quantum mechanical than previously thought. Some studies have also found evidence for quantum effects in neural microtubules, including quantum coherence in tubulin proteins and unusual electrical properties that might indicate quantum processing. While these results remain controversial, they suggest that quantum mechanics might play larger roles in biological systems than classical physics predicts. The Global Consciousness Project, coordinated by Princeton University, represents another approach to testing consciousness quantum connections. This project monitors networks of random number generators around the world to detect correlations that might indicate collective consciousness effects on physical systems. The project has accumulated decades of data showing small but statistically significant deviations from randomness during periods of global emotional coherence, such as major news events or natural disasters. While the effects are subtle and their interpretation remains debated, some researchers interpret them as evidence that consciousness can influence physical systems through quantum mechanical processes. Quantum biology research has revealed other potential connections between consciousness and quantum mechanics. Studies of anesthetics show that these drugs might work by disrupting quantum processes in neural microtubules rather than through conventional chemical mechanisms. The quantum theory of anesthesia suggests that consciousness requires quantum coherence, and that anesthetics eliminate consciousness by destroying this coherence. Research on quantum effects in bird navigation, plant photosynthesis, and enzyme catalysis demonstrates that quantum coherence can persist in biological systems under conditions previously thought impossible. These discoveries suggest that evolution might have learned to exploit quantum mechanics for enhanced biological performance, potentially including consciousness itself. The hard problem of consciousness, explaining how subjective experience arises from objective physical processes, might require quantum mechanics for its solution. Classical physics cannot explain why there's something it's like to have experiences, why consciousness has qualitative properties that seem irreducible to purely physical descriptions. Quantum mechanics introduces fundamental observers and irreducible measurement events that might provide the missing link between objective physics and subjective experience. Some philosophers and physicists have proposed that consciousness and quantum measurement are different aspects of the same fundamental feature of reality. In this view, every quantum measurement involves a primitive form of experience or observation, and human consciousness represents a complex organization of these elementary quantum experiences. This panpsychist interpretation suggests that consciousness is fundamental to physics rather than emergent from complex systems. Just as mass and electric charge are intrinsic properties of particles, consciousness might be an intrinsic property of quantum measurement events. Complex consciousness emerges from the integration of these elementary conscious events in the same way that complex physical systems emerge from the interactions of elementary particles. The measurement problem in quantum mechanics might thus be inseparable from the mind-body problem in philosophy. If consciousness is required for wave function collapse, then explaining quantum mechanics requires understanding consciousness. If consciousness emerges from quantum processes, then understanding consciousness requires solving the measurement problem. Recent advances in quantum computing have begun to shed light on these connections by creating artificial systems that manipulate quantum superposition states in controlled ways. Quantum computers can maintain coherent superposition states in complex systems while performing computations that classical computers cannot efficiently simulate. This demonstrates that quantum information processing is possible in principle, even if we don't yet understand how consciousness might exploit it. The development of quantum artificial intelligence might eventually test whether non-biological SYSTEMs can exhibit conscious-like properties through quantum information processing. If quantum computers develop behaviors that appear conscious, or if they begin to influence quantum measurements in unexpected ways, this might support the connection between consciousness and quantum mechanics. Brain-computer interfaces represent another frontier for testing consciousness quantum connections. As these devices become more sophisticated, they might reveal quantum effects in neural processing or enable direct interactions between consciousness and quantum systems. The ability to monitor and manipulate neural activity with quantum precision might finally provide experimental tests of consciousness-based interpretations of quantum mechanics. The consciousness connection to quantum mechanics thus represents more than an abstract philosophical problem. It touches on fundamental questions about the nature of reality, experience, and the relationship between mind and matter. If consciousness plays a role in creating definite reality from quantum indefiniteness, then understanding consciousness becomes essential for understanding physics itself. Whether consciousness collapses wave functions, emerges from quantum processes, or represents a fundamental feature of reality, the intersection of consciousness and quantum mechanics challenges our most basic assumptions about the nature of existence. The position paradox might ultimately be inseparable from the consciousness paradox. requiring new frameworks that can accommodate both the indefiniteness of quantum systems and the definiteness of conscious experience. Our next chapter explores how quantum information theory provides new perspectives on the relationship between indefinite quantum states and definite classical information, potentially resolving the paradox through computational rather than consciousness-based mechanisms.